Good evening, everyone. Celso Batalha here, Astro 10, Evergreen Valley College. And today we are getting together to go over some key points on chapter 15 that deals with Milky Way. Last week we introduced the different types of galaxies in the universe: spiral, elliptical, the irregular, and we saw the differences between those two or three types of galaxies and their content. Today we are focusing on one. That's the galaxy we live, the Milky Way galaxy. And I got online a YouTube video. Yeah, this one over here. The introduction is pretty cool, and I thought I would like to show here.
The Milky Way galaxy. A vast cosmic sea.
All right, so that's let me stop here. Okay, this is a rendering of our Milky Way galaxy. Why can't it be a real one? Well, you know, we happen to be somewhere in the spurs of one of the spiral arms called Orion, and pretty much 27,000 light years away from the galactic center. And have we left our solar system? No. Our solar system is the whole thing up to beyond the Oort cloud is not a light year, 1 light year, right? So we are pretty much confined to within 1 light year, and technology has taken us up to few astronomical units, but that's all. And so we can't be outside the galaxy. So the galaxy Milky Way, if you go from edge to edge of this galaxy, we are talking about 100,000 light years, edge to edge. And this place, the distance from where we are to the galactic center, another 27,000 light years. So this can't be us going out of our Milky Way and taking a picture. It's just a rendering, but it's very well done. And then zoom out. Now we are looking at our planet Earth, and there is something out there that might be the moon. Now it looks like star forming regions and star dying, supernovae or supernova explosion, and then the interstellar median getting reached by gas. Oops, that's a Lyra planetary nebula, the Ring Nebula in Lyra. That's a funny thing. But anyway, so I just thought it was cool to show that rendering. This is two galaxies, simulation of two galaxies colliding. That would be nice to be shown last week. But again, all of this is simulation. Anyway, this video, I can put the link in Canvas, and then you can take a look. In fact, I will save it, and then we can take a look there. I didn't look the whole thing, but the introduction was pretty nice, and then I want to show you. Okay, so let's go to chapter 15 and pretty much dive in our beautiful Milky Way galaxy. So if you happen to be in a very dark site, and this is not true if you are not. So if you are in our school parking lot and we can't see the Milky Way at all, but then you might ask, hey, you said we are part of the Milky Way. What do you mean by seeing the Milky Way? Well, when you go outside in a dark site or in a site that is bright, but not bright enough so we can see some stars, everything you see out there in the sky belongs to our Milky Way. Everything. Except if you are in a very dark site and you are able to see the fuzziness of a Andromeda galaxy. Because Andromeda galaxy is like another galaxy out there, like our Milky Way. In fact, is our companion galaxy, 2.5 million light years away. Or if you go to the southern hemisphere, if you go to Australia, New Zealand, Brazil, my country, and then you look to the proper direction, you might be able to see two fuzzy balls in the sky, and they are the Magellanic Clouds, the large and the small one. They are irregular galaxies that happen to be somewhat close from us. And then we can see with the naked eye, but again, it's just a fuzziness in the sky. We cannot resolve their content. We cannot resolve those stars if there are globular clusters and things like that in these galaxies because they are too far. Now, the same thing, the stars we see in the sky, they do belong to our Milky Way, but they are very close. If I launch Starry Night software, let's see if I can do that. There you go. If I launch the Starry Night software and I allow the time just to fly by a little faster, a little faster, a little faster. There you go. And the stars will slowly drift from east to west, like Orion is rising over there. You see the Pleiades, the moon is coming up. All these stars you can see right here. And by the way, my software has a bug because I can't see the fuzziness that goes along this concentration of stars that we call Milky Way. So, but all the stars you are seeing here drifting from east to west, they belong to our Milky Way, but they are relatively close, up to 3,000 or so light years, and then, but they are close. Remember, our Milky Way, as I described in the very beginning, in the opening of that video, is 100,000 light years. So 3,000 light years is really close. It's right there. So we don't see too much into the Milky Way. In fact, because our vision is blocked by dust that exists in the galaxy itself. But imagine our Milky Way is like a pancake, and we blueberry pancake, and we happen to be inside this pancake, probably orbiting one of these blueberries, looking across the dough. So we don't see too much because we have too much gas content in a way. But if you go to a very dark site, if you go to Yosemite Park, or if you go to, or if you happen to be like me in 1989, I was in Santa Cruz when there was the Loma Prieta earthquake. And when that happened, unfortunately, there was so much destruction, so many lives lost. But there was also power outage everywhere. So there was no light. And the sky were beautiful, and you could see Milky Way, you could see everything because it was pitch dark. So if you go to a site that is relatively dark, no light pollution at all, you might be able to see these features going across the sky from one horizon to another. And going all the way close to almost your straight up position, your zenith, and then going down to the other side. So that is the Milky Way. I mean, classically it's called the Milky Way, this fuzzy patch of whitish display of stars. They are so far away we cannot resolve them. But across those whitish clouds, you see this dark patch of dark clouds. Okay, that's the Milky Way galaxy. It's a better picture here and there too. Now, depending on how if you have a photographic camera, with digital or in an old style with a chemical emulsion, which is pretty much the technology of grains, you can allow for light collection for more than a few seconds. And if you let the shutter open for relatively few seconds, you might be able to resolve better the display of this, what we call the Milky Way. But again, the Milky Way is everything you see, but if you look across in the direction of the pancake dough, then you might be able to see this nice fuzziness here, and that is what traditionally is called the Milky Way. If you don't look with your optical eyes or with optical technology, but if you use radio waves, or if you look with a different type of wavelength band, color band, you might be able to detect different features. The fact that you in this picture here, you are pretty much taking a picture of the Milky Way using R. R stands for radio wavelength. So you are probing a gas that is able to produce this electromagnetic radiation, which has the lowest possible energy content, which is the radio wave, that can only be produced in gas that is relatively cold, and this gas exists in the interstellar medium, and more so in the spiral arms of the galaxy. So when you take images using radio telescope, you'll be able to see with more detail the features of our spiral galaxy. And the reason for that is, since the gas is undisturbed, there's not a lot of collision, not a lot of interaction in this gas. Certain transitions, they are usually very difficult to occur in the laboratory here, or even in gas that is part of a planetary atmosphere, which is relatively dense when you compare with gas in the interstellar medium. So certain transitions, certain features that are associated with transitions of hydrogen specifically, that's what I want to go, occur because there is not a lot of interaction, not a lot of a collision, gas collision. So because the gas, the molecules, and in fact the atoms are not colliding so frequently, the so-called 21 centimeter transition line can occur. And that happens when an electron that goes around a proton change the orientation of its rotation. So, and when the spring goes, the rotation, if you think of electron as being a kind of a little hard ball that rotates, when that rotation switches direction up and down, it pops this color band, this radiation that is typical of 21 centimeters, and astronomers use that information to map the regions where this gas is glowing. And by doing so, astronomers can make a very detailed map of the galactic disk and the galactic arms. Why is that? Well, because the galactic arms and disk is so full of dust that we don't see it properly using optical light. Our eyes, if you will, or light that our eyes are able to capture, or the optical telescopes we have in the observatory, they don't work well to detect features that are so far away into the galactic disk because their light, their illumination, their information, if you think as light as being information, that information has been lost as it traveled towards us, because the dust in the interstellar medium has depleted, has collected that information and subtracted out of being, and we don't receive it. But the 21 centimeter line has a strong penetration power and can go through the dust without being absorbed. So which means astronomers can use that light if they have a telescope that allows them to see further into the galaxy. They have this radio telescope, they can use it to really map features in the galactic disk without doing what that simulation that I show in the very beginning does, which means take you out in space and then look down in the galaxy, which we cannot do. There's no technology for that right now. But telescopes, especially in the radio band, allows astronomers to do that. Now let's talk about globular cluster. So globular clusters are the galaxy, as you can see here. Before we go there, it has this spiral structure with 4 or so arms that comes out of this bulge. So this is not, again, a picture of Milky Way, right? So it's a galaxy, it's a spiral galaxy that has a bar-like structure going through this bright region we call the bulge, right here, this bulge. And this bar-like structure, out of which come these spiral arms so well defined. And our galaxy is supposed to be not so much different from this galaxy here. I don't know the name of this galaxy. It's somebody's galaxy, some galaxy, out there in the space, among trillions of other galaxies, and I'm just showing one to you, probably with 100 billion stars and God knows how many solar systems in there, and God knows how many aliens are happily living in there. But what I'm trying to say is that this structure has this bulge, the central bulge, has the spiral arms coming out of the bulge, and the distribution and the velocity, the pattern of stars in it, or happen to be different depending on where you are. So if you are in the disk of the galaxy, all the stars and the gas happen to go around in a very definite way, as opposed to the stars that happen to be in this bright area we call the bulge. They go around the center in any way they please. In fact, it depends on how exactly they were formed. Now, the galaxy is surrounded by a region that has a radius that is 3 times as big as the radius, as the spiral structure itself is the halo. And the halo, you can find old stars concentrated in what we call globular clusters. So globular clusters are hundreds of thousands of stars tidally locked gravitationally, which means once these globular clusters were formed, pretty much when the galaxy was being formed, they don't let it go, the stars that are part of them. Like our sun and maybe stars that are part of Pleiades clusters or any open cluster in our galaxy, these stars are pretty much free to go once the cluster itself evolved. Globular clusters are not like that. Since they have so many stars, the gravitational well in that cluster is so intense, the stars are unable to leave the cluster and they stay there forever. So clusters, globular clusters, are the way they are since they were formed. So you have a bunch of sibling stars, they are coeval, they were formed at about the same time, but they evolve differently as we studied in stellar evolution. The more massive stars, they go faster through their evolutionary sequence, whereas stars that are not so massive, the low massive stars, they take a long time to go and achieve their end of line in evolution. So globular clusters, very important. And globular clusters can be used, as we studied in stellar evolution, to determine. So in case you observe with sufficient detail all the stars in a cluster and you build what's called an HR diagram on it, with a diagram that relates surface temperature and their energetics, or the energy that comes out of them, you can, by measuring this turn-off point right here, see, you have the main sequence and you have the giant phase. So this turn-off point here, physicists and astronomers can calculate how long would take a star of a mass corresponding to this point to finally leave the main sequence. So we can use that time, the time the star takes to initiate its move out of the main sequence, we can use that time to determine how old the cluster is. And when this is done, we realize the clusters are old. They are pretty much structures formed when the galaxy itself happened to be formed. Okay. Now, all the clusters, globular clusters that have been found, they in fact, Harlow Shapley, in the beginning of 20th century, observed and worked with this globular cluster, and he did some important discovery, and that was he found stars in it. There was pulsating stars, R Lyra, and I think we discussed these stars last week. So R Lyra, let's see if I have the name of them here. There you go, R Lyra. So these stars, they have something interesting. They pulsate in such a way that the time it takes them to pulsate corresponds to their luminosity. So, in other words, if you observe these stars with some detail, you notice that they go in a pulsating range, right? So this time here is the time of pulsated. So if this is brightness, so in R Lyra, this time of pulsation is always the same and usually less than 1 day. Usually less than 1 day. And what astronomers knew at that time, that if you observe and find an R Lyra anywhere, and you measure this time of pulsation, you can determine what of these stars. You can determine their luminosity. Oh, how important that is. So it's important because if you know the luminosity of any object and you observe them to the point of getting their brightness, the inverse square law, right, that relates the brightness you observe with the luminosity, which the energy the star itself, the R Lyra itself is putting out, it enable you to determine the distance, right? So you have, in fact, an equation. The inverse square law gives you an equation of two parameters. They are supposed, in fact, the 3 parameters. So in the case of R Lyra, you have information about 2 of these 3 parameters. Brightness, because you can observe, and luminosity, because of the period luminosity relationship. And from there, you can pretty much access distance. So what Shapley did, he found and he mapped all the globular clusters, and he found R Lyra on them, and he was able to establish distance to these objects. And based on where they happen to be located, he developed, and this is a better determination than Harley Shapley had, but he could determine the position of these globular clusters. And what he found was these globular clusters, in fact, were not orbiting us, our region in the Milky Way. These globular clusters were gravitating around some region which Harlow Shapley fixed as being the center of the galaxy. So he said, well, there is so many globular clusters, and they happen to be all clustering around a point, and that point was seen in the direction of the constellation Sagittarius. And then what he said was, well, since these globular clusters, with comprised of hundreds of thousands of stars, happen to be all going around that region in the sky right there, then he claimed that region as being the center of the Milky Way galaxy. So towards that region in Sagittarius, he claimed the center of the galaxy is somewhere in there. And later on, it was found that he was completely right. And then he became the big Harlow Shapley. Then he made some mistakes later, especially when debating with Curtis if whether or not the nebulae, all nebulae seen in photograph plate in those days were belonged to our Milky Way galaxy. And he thought they did, and Kurt said no, and finally Hubble, the big Hubble, was able to settle the debate when he found Andromeda. Okay, but going back to clusters, so we in our galaxy we found globular clusters that happen to be in the halo going around the galactic center, but there are also open clusters, and these open clusters they have much less stars, hundreds of stars, and which means the gravitational pull, the attraction of these stars is not so intense. So once these stars evolve, they are coeval, they form at the same time, but as they evolve, they spread out and they abandon the clusters. Some astronomers think that our sun was a member of an open cluster and now is in an independent stars, like kids, right? So they are born in a house, and yeah, they 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 have mom and dad and or somebody supporting, and then next thing you know, when they become mature, they are out of there, right? They go conquer life. That's the cycle, human cycle. But anyway, open clusters are much younger because they are recently formed, than globular clusters. Again, open clusters, once they are formed in few million years or 100 million years, they disperse because the stars don't stay together that long. Whereas globular clusters, since they have much more stars, once they are formed, they stick together, right? They don't disperse, which means when you observe stars in these clusters, they are relatively old. Globular clusters are not being formed anymore. They were formed when the galaxy itself happened to be formed in the very beginning of life. Not life, our universe. Um, Now, and I think those are kind of key points. And the last one is dark matter. So, what is the mass of the galaxy and dark matter? What the heck is dark matter? Well, when you look at data collected from stars and interstellar medium gas alone, and you see the galaxy mapped the way it is with the spiral arms and the region between spiral arms and everything, we think, okay, that's our Milky Way, and that is what is the mass that I observe, which means the mass of the stars, the planets they have, and the interstellar medium in between the stars. That mass is the one responsible for creating the gravitational force that is, in its term, responsible for driving all the stars around the galactic center. That's not the case. And the reason is when you observe stars, they're going around the galactic center, but way beyond the region where we are in the solar system. So we are somewhere here. So beginning this point, and according to Kepler's law we studied previously, the speed in which these stars further out, this is distance to the galactic center, right? So the orbital speed in which these stars go around the galactic center would fall according to Kepler's law, and what we observe is they don't. They just keep rising. It's a big flat thing. Now, either Newton's law is wrong, so you have to say, hey, Newton, Sir Isaac Newton, 1700, your equation GF is equal GMM divided by D squared is not correct. You should, fix it. But to say that, you might be able to claim, but you have to explain why, and more so, you have to explain why it works. To send a probe to Jupiter and other, So Newton's law worked quite well, by the way. So we think it's doing the job, because we haven't found any situation in which it doesn't. So either Newton's law is wrong, in which case you have to provide some alternatives to it. But as far as I know there was an astronomer in Israel when I was in my graduate courses, and he was proposing some parametrization of Newton's law that would have a couple of terms. One would fall with the square of the distance, like the one we know, and another one who would fall, I think, with the third power of distance, or 50 power, something like that, and would kicks in certain conditions. And but I didn't see that advancing since then, and that was a long time. But anyway, so either that, or another way to explain is, well, if the galactic halo, which means something that has a diameter of 300, in fact, 150,000 light years in radius, diameter 300,000 light years. So if the galactic halo is populated by something that we don't know what it is, but it has mass, it is able to exert gravitational pull. If that is true, then we can explain this orbital curve. We can explain this thing here. Okay. Now, in 1930, another astronomer, Zwicky, he was, in fact, the first one who proposed the existence of these dark matters, as he studied groups of galaxies that were too close to one another and yet moving too fast, to the point that if there was not an unseen matter holding them in place, these galaxies would have flung away, and the cluster wouldn't exist. So as if they were tied together by some mass kind of embedding them. And then he proposed dark matter, and he was kind of criticized and ridiculed because he was Zwicky. But he seems to be right, and he opened some sort of pathways to a revolutionary idea, which now we call dark matter. And there are candidates for dark matter. It's when I was a graduate student, they were talking about black holes, tons of black holes in the galactic halo, because you don't see them, right? So the dark matter can't be something that interfere with observation. So you don't see it. It doesn't subtract light from faraway galaxies, or you would detect that. So what, you don't see it? Okay, dark black holes. But black holes, if there were many black holes, we might have had more metals in a galaxy than we would think. So black holes was a suggestion, but didn't move too far. There are other candidates like small planets that never formed. They are called massive galactic compact massive machos. Is machos. What is a machos? Massive compact halo objects. Massive compact halo objects. I think that's the short for machos. So machos could be, but the investigation done to find these machos resulting in no good candidates. They found brown dwarfs. They found some possible planets using gravitational lenses, but that's not enough to explain the mass required or the gravitational pull required to explain orbital motion or dark matter. A fine candidate that is thought about now is the so-called WIMPs. Weakly interactive massive particles. And these WIMPs, they are currently being tested in laboratory in the Large Hadron Collider in Europe, and the idea is these massive particles, they come in and out in a short time scale. We do not detect them, but if you add together all these WIMPs coming in and out, it might give enough mass to explain the rotational curve in our galaxy. So, what is the point of dark matter? Well, 90% or more of the material required to explain the dynamics of our galaxy is something we don't know. And with that, I close this this chat. So let me know if you need anything.